Let's take another scenario here. Point mass. Let's look at the mass and perspective of mass, like in quantum mechanics and then in gravitational theories. So we use mass more in gravitational theories rather than in quantum mechanics. So the gravitational theory is the mass of an object remains same no matter whatever you do with the object. Let's take this object A, and this is some object. Like let's suppose it has 1 cubic meter of volume in that sphere. Then if you expand the same object to a size of 1 cubic meter, or meter cube, and then this is 10 meter cube, and so this is so another object. You expand that object to 10 meter cube, to internal structure of the object expands. And then you compress the same object to a point size object. So gravitational theories and the definition of mass is that all these three objects will measure the same amount of mass. We can say like right here, A is M1 and B is M1 and C also is M1. All three objects are having the same amount of mass. And when we take when you come into the quantum mechanics, and there is some term pops out called like a mass deficit. So because of that, when you take certain amount of nucleons, let's say the nucleus, let's take this is one of nucleus of an element, and it has 40 nucleons. So mass of that object, let's say M1, and let's say another nucleus which has same number of nucleons like protons and neutrons together, it has same number of nucleons. Then let's say mass of that object is M2. Then this object is bigger than this nucleus is bigger than this, and then this nucleus is bigger than these two nucleuses. And then let's say it too has the same number of nucleons, 40, and then mass has M3. So this is 3. So how these three masses relate to each other? When you say M1, M2, M3, the mass and as the object, as the nucleus has more and more binding energy, like the iron and nickel, that particular nucleus will be more compact nucleus. As the nucleus becomes smaller and smaller and smaller, it will have more and more binding energy within the nucleons within that nucleus. So if the binding energy increases, it will measure more in mass, because according to the mass energy equivalence principle, energy is mass. And if that object has more binding energy, it measures more amount in mass. So when you compare these three objects, like M1, because this is a compact nucleus than this one, so all the protons and the neutrons are more packed together closely in this nucleus, so it will have more binding energy. The mass of this nucleus will be more than the mass of the B. So mass of M1 will be greater than M2, and at the same time M2 will be greater than M3, because all the nucleons are loosely packed within this nucleus. So therefore, when you say like M3, mass of this C nucleus will be less than M2, and the M2 will be less than the mass of the M1. So let's suppose what happens when you compress all these nucleons, all these 40 nucleons to a point size. A nucleus will measure more in mass, because the point size will have tremendous amount of binding energy within the nucleus. If they are that close within the nucleus, there will be tremendous amount of binding energy. All the binding energy, according to the mass energy principle, is mass. So this particular nucleus will measure more mass. So let's suppose M4. So M4 will be greater than all these three together. So M3 less than M2 less than M1 less than M4. So M4 will have more mass among all these nucleuses. So one more thing with the M4 is there won't be any mass deficit. Means like the total number of total mass of the nucleons within that nucleus will be equal to the mass of this nucleus. So there won't be any difference between the mass of the nucleons and then the nucleus of the mass of the nucleus. Here there will be lot of difference between the total mass of the nucleons and then the combined mass of this nucleus. So what exactly is happening in quantum mechanics perspective about mass, and what exactly is happening with the mass in perspective to the gravitational theories is totally contradicting to each other. When you compress a nucleus, it gains more and more and more mass. When you compress an object in gravitational theories, it remains same. Even if you compress that object to the size of a nucleus, still remains mass remains same. So when the matter goes compressed to the size of a point, then it will have more and more mass. So there is here one is, what is the basis for this definition actually, definition of mass? Did anybody compress an object to point size and measure the mass, and did anybody expand an object and see like both all these three forms of the same object are measuring mass? No, nobody did experimentally test this definition of mass, and that is totally baseless and imaginary concept. And this is what exactly happens with the mass. Is this the practically observed thing that is happening with the mass? Mass, when you compress an object, when the matter comes closer and closer, the amount of gravity that object exerts to the amount of gravity Earth exerts on the object will increase. So as the object compresses to smaller and smaller size, it will measure more mass towards the gravity. It measures more mass and more gravity to the Earth. So the definition of mass is totally baseless, and the true representation of mass is the mass measures more when it is compressed. So that covers the second topic on this presentation.